Okay, welcome back. Now it's time for the second tutorial lecture with Fay Dowker, and she's talking about the path integral approach to quantum mechanics.
Hello everyone. Thank you to Matt and Alan for organising this meeting. So in the interest of building community, I want to at least introduce the people from Imperial to you. So let me see, I'll start over there. So Jonathan Halliwell. I'll include you, James, because you were at Imperial. James Earsley, who's now in Cambridge, and will be speaking this afternoon. Dionigi Benincasa is a graduate student. Joe Henson is going to be at Imperial next year, hopefully. And Michael Buck is also a graduate student. And Daniel Beddingham is a postdoc. And we all work on foundations, so I think it's a British group, and it's nice to meet everybody here. So I'm going to talk about the path integral approach to quantum mechanics. And here's the plan of my talk. So I'm going to point out to you something that isn't generally known, that in 1932, Dirac wrote a paper, and he set out in that paper a fork in the road, that a decision that one has to make in pursuing quantum mechanics, and the fork is whether to pursue it in a relativistic way or pursue it in a non-relativistic way. And I'll give you some quotations from that paper and explain what that means. And then I'm going to show you that taking the relativistic branch of the fork, in other words, taking seriously the fact that physics is relativistic, the world is relativistic, leads you to try to found quantum theory on the path integral rather than on Hilbert space. And I'll argue that as far as the textbook theory is concerned, so what I mean by textbook theory is just predict the usual Copenhagen rules for predicting the results of experiments, of measurements, the path integral does just as well as Hilbert space. You can replace the Hilbert space by a path integral fundamentally. You can actually recover the Hilbert space, but you can do everything that you can do with Hilbert space with the path integral. However, the path integral gives you a natural way to go beyond the textbook, and if you like, one could characterize foundations of quantum mechanics in general as the attempt to go beyond the textbook. And another way to put it is that we want a quantum theory in which there are no divisions between quantum and classical physics, a unified quantum theory of closed systems where there are no external classical measuring apparatuses or classical observers. And the path integral does indeed allow you to go beyond the textbook to define a quantum theory of closed systems without appeals to external classical measuring devices, measurement agents, or anything that's not quantum. And in considering that foundation for quantum theory, one is led to another fork in the road. There are actually two different attitudes that one can take to a path integral formulation of quantum theory that exist in the literature. I'm not going to claim that there can't be others, but at least in the literature as it is today, there are two approaches, and you can choose. And they have different. I'll sketch out what the differences are between them, and then I'll end with some talking points. Okay. So the paper that Dirac wrote, it's actually, he submitted it in 1932, but he was published in 1933. So very soon after the discovery of quantum mechanics, he wrote this paper. It's called the Lagrangian in quantum mechanics. And these are direct quotations from that paper. So he says, quantum mechanics was built up on a foundation of analogy with the Hamiltonian theory of classical mechanics. And that's undoubtedly true, and no one is more closely associated with that than Dirac himself. So there is indeed a remarkable analogy between classical physics in its Hamiltonian framework with canonically conjugate variables, position and momentum, and Hamiltonian function of those classical phase space variables. There are canonical transformations of those variables to other canonically conjugate pairs of variables, and the whole Hamiltonian theory is beautifully invariant under these canonical transformations. And that has its exact mirror in the Hamiltonian formulation of quantum mechanics. The variables, the phase space variables, become operators, x hat and p hat, and the Poisson bracket structure of the Hamiltonian classical theory becomes the commutator structure of quantum mechanics, and canonical transformations become unitary transformations. Okay. But Dirac says there is an alternative, and it's provided for classical physics, and that's provided by the Lagrangian. So that's an alternative framework for classical physics. And he says there are reasons for believing that the Lagrangian one is more fundamental for classical physics. And why is that? He picks out two reasons. One is that there is no action principle for the Hamiltonian theory, so that the action principle for classical physics is expressed in terms of the Lagrangian. You vary the Lagrangian by a small amount, and you require that the variation be stationary, and that gives you the equations of motion. And the second thing that Dirac, second point that he makes is that the Lagrangian method in classical physics can easily be expressed relativistically, while the Hamiltonian method is essentially non-relativistic in form, since it marks out a particular time variable as the canonical conjugate of the Hamiltonian function. So he says the Hamiltonian method is essentially non-relativistic. And one can see that carries over to an essentially non-relativistic character that the usual textbook canonical quantum theory based on Hilbert space with operators which are the quantum replacement for the x and p hat variables of the classical theory. Okay. And then Dirac shows that the Lagrangian approach, so if you take the Lagrangian approach to classical physics and you ask what is it the analogue of the Lagrangian approach in the quantum theory, and he shows that it leads to the path integral. Essentially he gives all the steps for constructing a path integral, which of course was taken up later on by Feynman. So I'm going to call the path integral the Dirac-Feynman path integral. So the Lagrangian approach leads to the path integral, and that is expressed in the following. So here, this is the propagator. So it's the amplitude. Suppose that you measure the part, and I'm going to concentrate for most of the talk on a single particle in non-relativistic particle in one dimension. Okay. So you measure the particle at position x at time t. What's the amplitude for it to be measured at position x primed at time t primed? Well, I just define this k to be the propagator. Is this inner product here? So it's this amplitude here. And the Dirac-Feynman path integral says that this propagator is a sum, an integral over all the paths that can be taken gamma from x at t to x primed at t primed. Each path is weighted by the exponential of I times the action in units of h. The picture is this. So it's non-relativistic. So here's x, here's t. You start at some time t. Oops. Label those axes. So this is at x. You start here at time t primed. You end up here, and you consider all possible trajectories that go forwards in time between x at t and x primed at t primed. You calculate the action, given at, and the action is the integral of the Lagrangian from t to t primed. You weight each path by this complex, this weight, and you sum them all up. Famously, this path integral is not rigorously defined as an actual integral over some path space. However, one can simply define this path integral in a limiting fashion. So this path integral is actually, its definition is this. You define it as a limit as a large, what you do is you divide up the time interval between t and t prime into a number n of equal time steps. And you calculate, for each of the little time steps, you calculate the classical action of the action of the classical path that goes from some initial position x prime at t prime to some intermediate position x n minus 1 at one time step. I should go the other way around. So you start at xt and you go to position x1 at a time t1, which is one of these small time steps later. You calculate the classical action for the action of the classical path between those two endpoints. And you weight that little segment by this. And you do that for all of the little segments. You integrate over the intermediate positions, and you take the limit of that as n goes to infinity. And that's what this path integral is defined to be. Okay. So are there questions?
Can I ask?
Yeah.
So do the paths cross? Looks like they cross the way you drew it.
Yeah, they can go anywhere.
So when you're at the crossroads, how does it know where to move next?
It's a sum over them all. So
Right.
it doesn't. So it's a sum over every single. Any other questions?
They just keep going forward.
They have to go. Yeah, in the non-relativistic theory, they go forward. Okay. All right. Now, the following is going to be entirely within textbook, ordinary textbook quantum mechanics. Let's consider a sequence of measurements at times t1, t2, up to tn, and they're measurements of some observables. You can ask, what's the probability for a particular outcome for the first measurement at t1, and then followed by a particular outcome for the measurement at t2, followed by a particular outcome for the measurement at t3, etc. And that can be calculated in the usual textbook, with the usual textbook rules about projection and collapse of the wave function. And the expression that you get is the following. Psi is the state of the system. You apply to that state a projection operator, which is the projection operator. So say you want to ask, is the outcome in a particular region of the spectrum of the operator? So are the outcomes of a certain particular set of values? Well, you construct the projection operator onto the subspace of the Hilbert space, which is the eigenspace associated to those particular eigenvalues. You construct that projection operator at time t1, so it's a Heisenberg operator. It depends on time, so it's that projection operator t1. And you apply it to this state. And then you do it for all the subsequent measurements. And you get what you could call some kind of projected state. It's projected by the appropriate projection operators for the particular outcome that you're asking the question about, sequence of outcomes that you're asking the question about. Then you take the norm squared of that vector, and that's the probability that the outcome of the measurement 1 is in this particular range, which I'll call delta 1 of possible values. And all the other outcomes are in their particular range. And you can generalize this to mixed states. Instead of this formula, you get a trace formula where you replace psi by rho, and you can also generalize it to generalized measurements where instead of projection operators you have positive operator value measures. Okay, so it's a 2-minute proof. To do that, I recommend that you have a go at it if you haven't seen this formula before, for the probability of a sequence of measures in the using the usual Copenhagen rules. As I said, the projection operators are Heisenberg operators. They depend on time in this way. U is the unitary evolution operator that takes, here it takes you from T0 to Ti for the ith measurement. And in this, you can re-express this Heisenberg picture formula in the Schrödinger picture. So you just replace these time-dependent projection operators by their time-independent Schrödinger forms, and these unitary evolution operators come out in this way. So in this picture, it looks like you have the state at some time t0. You evolve that state from time t0 to t1. This u10 is just that. It's the unitary time evolution operator that takes you from 0 to time t0 to time t1. Then you project onto the range delta 1 for the values of the outcome of the first measurement. Then you evolve from time t1 to time t2, then you project again using the Schrödinger projector. You carry on going, and at the end you get the projection p delta m onto the last range, and then finally a unitary time evolution operator that takes you from time tn, the time of the final projection, to some arbitrary, and it doesn't matter what, time tn plus 1 to the future of tn. Okay, so that's a simple. Okay, so all of that was just standard textbook Hamiltonian Hilbert space manipulations. Okay. In the special case of a non-relativistic particle in one dimension, and we can generalize to higher dimensions and we can generalize to many particles, but just for simplicity of notation, I'm just going to focus on the simple case of one particle in one dimension. When the measurements onto ranges of positions, so the idea is that there's some A and some B for each measurement, there's some range, this is an X, between AI and BI, and you're asking the question, when I measure the position of the particle, is it in this range or not? And the projection operator that's associated with the particle being measured in that range is this. So it's just an integral from x's AI to x's BI of this back-to-back operator, xx. And if in that expression for the probability of a sequence of measurements, you just replace all of those Schrödinger operators, p delta, with these projections onto ranges of position operators, and you insert decompositions of the unit of the unit operator everywhere you can put them, and you use that the position representation of the unitary time evolution operator is just the propagator, then that expression for the probability of that the outcomes of a sequence of measurements are certain values is given by this thing. So let me just draw the picture. So here's x, it's t. And you have a certain number of times. So t0 is the initial time. And then you have a measurement t1, a measurement t2, etc. up to tn. And you ask, is it, this is the initial time. So t1, you ask, is it between a1 and b1? And at time t2, you ask, is it between a2 and b2? Is it measured to be between? And then tn, is it between a and bn? projection operators associated with these ranges. Then this is what the probability that the answer to this question is yes, it is measured to be between A1 and B1, A2 and B2, A1 is this. It's just the usual thing. You have a wave function at t0. You propagate it to time t1. Then you propagate it to t2. Then you propagate it all the way along. You finally propagate it to time tn. But you have to project. Where did the projection operators go? The projection operators became restrictions on the ranges of the intermediate integrals. So you propagate from x0 to x1, but x1 is only allowed to be between A1 and B1. That's where the projection operators go. So that fundamental formula becomes this integral expression. This is still a vector, notice, because there's a ket here. All right, but you notice we have propagators here, and according to Dirac and Feynman, these propagators are actually path integrals. They are sums over histories. So now we can replace these propagators by path integrals. And also, you can see that this is the norm of a state, so squared. So what we do is, if you take this state and take its inner product with itself, that's its norm squared. So if you do that, then what you get at the end is that this probability is equal to the following thing. It's a double path integral, or a double sum. It's the sum over all paths in a set that I've called delta. And delta is the following set. It's the set of all paths that start anywhere here, so it can start at any position at time t0. Go through A1, B1, A2, B3, A2, B2, A3, B3, etc. And then end up anywhere at all at time tn plus 1. So these two ends are free, but they're constrained, the paths are constrained to go in between these gates. And this is the set of paths delta, and I'm going to write it here because I refer to it several times. So this is delta. Set of all paths passing these gates. Okay. So the probability that delta is measured is given by this double sum. As I said, it's a sum over delta twice of this object, which I call d gamma primed gamma. So it's a sum of d gamma prime gamma, where you sum gamma primed over all paths in this set delta, and gamma also over all histories in gamma runs over all of the elements of delta. And what is this object here? The integrand is this. It is the complex weight e to the minus I times the action for gamma primed times e to the plus I times the action for gamma. And you can see that that's going to come about because you've taken the inner product of this path predicted state with itself. So one comes from rho and one comes from the ket. That's why they're complex conjugates. That's why this is a minus I here and that's a plus I. Times the weights, the complex weights of the initial position. So psi of the initial position of gamma primed, where gamma prime starts at time t0, complex conjugated, times the weight of the complex weight of psi, where psi starts at t0, times this delta function, which means that the two endpoints have to be the same.
You're missing a prime?
I'm missing a prime, thank you. Yeah, so there should be a prime. So the two endpoints have to come together. Okay, so that you can express this probability for that, the particular outcome of a sequence of position measurements as a path integral. Okay, well what about other observables? That's very special to position. Okay, what about other observables? So I'm going to make a claim here, which is that only ideal measurements of position are realistic for quantum mechanics. And I haven't said this before, but this whole structure of the Copenhagen rules is for ideal measurements, measurements which leave the state in an eigenstate of the observable that you're measuring. If it starts in an eigenstate, then it will leave it in an eigenstate. But if you're considering the textbook ideal measurements, then only measurements of position are realistic. And therefore, the path integral is sufficient for textbook quantum mechanics. Okay. Of a spinless particle. I'm not saying anything about spin. So why do I say that? Okay. So here, I've titled this Against Phase Space in Quantum Mechanics. So phase space is essentially non-relativistic as Dirac, for the reason that Dirac said. To define the phase space, to define your Hamiltonian, you have to pick out a particular time variable, a particular choice of time. And that's essentially non-relativistic to do that. And what that does, and if you build quantum theory based on the Hamiltonian in a canonical way, this non-relativistic character shows up. It shows up in the quantum theory as non-local signaling. Okay, I'll show you that in a minute. Position and momentum are not on the same footing physically in quantum mechanics. Right, this is not a mathematical statement, it's about physics. So physically, position and momentum are really not on the same footing. It's not the beautiful thing you learn about different bases being unitarily transform bases being equivalent in quantum mechanics is not true as far as physics is concerned, where by physics I mean measurements. Okay, so here's the example that shows that position and momentum are not on the same footing. Let's consider two local measurements of position. So this is t equals 0. I'm going to consider some earlier time, t equals minus epsilon, and some later time, t equals plus epsilon. And consider two measurements of position. And I want them to be their local measurements, but they're non-local to each other. So there's a measurement here of position, and the measurement is the part that you're measuring, whether the particle is in this little range here or not. And the projection operator I'm going to call A, traditional. And then at time t equals epsilon later, I'm going to consider projection onto position. Again, a local measurement, and it's the projection operator associated with that is B. These are Heisenberg operators. This depends on epsilon time, and this depends on time. Okay. All right. Now, the agent, Alice, can either do her measurement of position or not. And the expectation value of Bob's measurement depends on whether Alice does her measurement or not. And it depends on it because the wave functions spread. Okay. So if Alice doesn't do her measurement, then the initial state is not projected, and the expectation value of this B measurement is whatever it is. If Alice does her measurement, that collapses the state onto an eigenstate of A, and the expectation value of B, given that measurement was done by Alice, is different. However, so that non-local signaling goes away, it tends to 0 as you take epsilon to 0. So if these measurements become closer and closer and closer in time, the signaling from A to B tends to 0. And in the limit, where these measurements are all at t equals 0, because A commutes with B, the expectation value of B is the same, whether or not Alice does her measurement. So this is what I'm saying here. So Alice can signal to Bob, but that signal tends to 0 as epsilon tends to 0. So this is the expectation value of B if Alice doesn't do the measurement. This is the expectation value of B if Alice does do the measurement. It's the sum of the expectation value when she gets outcome yes for her measurement, plus the expectation value of B if she gets the answer no for her measurement. And these two are in general different if epsilon is non-zero, so there's signaling. However, because A and B commute as soon as epsilon goes to 0, so they only approximately commute when epsilon is small, but they completely commute when epsilon is 0, you can just commute this A through. A times A squared is A, so you get BA here. You can commute this 1 minus A through, you get B times 1 minus A, and A plus 1 minus A is 1. So this whole thing, this thing in the square brackets is just the expectation of B, so this becomes 0. Okay, yes?
There's a problem here because if epsilon goes to 0, it means that you are measuring the time with infinite precision, and then you lose all information about your energy, which means that such a measurement in effective is not possible because your energy can be also infinite.
Okay, so this is an idea. This is the way to model a measurement in the framework of ideal measurements in the textbook theory. And what this shows, I claim, is that that's good and okay for position. So that we can adequately model position measurements in this way. That you don't get any unphysical, non-local signaling from it. All right. Now let's add a third measurement, and that's going to be a measurement of some observable and the associated projection operator is C, and that measurement is going to take place here. And if that measurement C is onto position again, so it's some measurement of position, the range can be anything you like, so it's just a measurement of position again. And you definitely do that measurement. That's not a decision to be made by anyone. It's just that that measurement is definitely done. Then again, exactly the same calculation shows that as you take epsilon to 0, A, B, and C all commute, and therefore the expectation value of B is the same whether or not Alice does her measurement or not. So the expectation value. So Alice cannot signal non-locally to Bob. Okay. You can probably guess what's coming next. If that intermediate measurement is not onto a range of position, but is onto a range of momentum, then this is no longer true. And in fact, it's no longer true even if your observable is some intermediate thing between positions, intermediate rotated operator between position and momentum. It's no longer true. You can calculate the difference in the expected value of B if Alice does her measurement and if she doesn't do her measurement. And that remains finite now as you take epsilon to 0. So there is non-local signaling if you can do this ideal measurement of momentum. So what's the conclusion? The conclusion is, just in a similar way to you were saying, that ideal measurement is just a bad model of an actual intervention, actual physical intervention in this system. You shouldn't be able to do it. You can't model it as an ideal measurement. You cannot model measurement of position of momentum by ideal measure by the usual textbook rules. Now this simple example can be generalized to the context of relativistic quantum field theory. And you can show that, for example, one particle's states cannot be measured by ideal without causing superluminal signaling. So this is really the essential point. But this superluminal signaling has its non-relativistic residue is the fact that you get non-local signaling in the non-relativistic. So this beautiful transformation theory, which asserts the equivalence of unitarily related bases in Hilbert space, is ruined by this law of locality. You don't believe that we can signal non-locally or superluminally. Then there is a difference between position measurements and momentum measurements. They're not on an equal footing physically. And we could say that, well, position observables are the physical ones. And indeed, one can argue that to measure momentum, you have to measure the position at one time and the position at a later time, and that's what you do when you measure momentum. But one could have reached this same conclusion already had we, from the start, chosen the relativistic Lagrangian fork in the road and based the theory on the path integral. There, the path integral gives you the probabilities for sequences of position measurements, and that's what it fundamentally gives you. And that, I claim, is sufficient for quantum mechanics. Are there questions?
Yeah, so the reason that this doesn't work, the momentum is essentially the P is sort of like dx by dt, and the dt is like an epsilon downstairs, which cancels out.
You can think of it. Yeah. It's non-local.
In your simple argument, you considered a conditional measurement of Alice as a particular projector. But does the argument also hold if you don't condition on a particular outcome of Alice's measurement?
Oh, you don't condition on a particular outcome. You're not conditioning on. It's just conditioning on the fact that she does the measurement. Okay, because this is a sum, right? So this is where she gets the outcome 1 or yes. And this is where she gets the outcome 0 or no. So you're conditioning on the fact that she does the measurement, but not on the outcome.
Are you making a claim about what the fundamental measurements are in the relativistic field theory case?
No, that's an open question. So which is remarkably, it's remarkable that it's an open question. So if you want to be sure that you cannot signal superluminally, the observables that are safe to consider are observables like this. So phi of x will do. That's local, that's appropriately local. And any smearing of phi of x on a space-like hypersurface, so you can take integral x, some f of x, on f of x. So let me put in, so this is position over some t equals constant size. Something like that is also safe, but is in fact not known whether a space-time integral, whether if an ideal measurement of an observable like this would cause superluminal signaling. So that's a remarkable situation, because these are in fact the observables that people base quantum field theory on in what's called in the algebraic approach. So if you integrate these over some open region of space-time, then these smeared space-time smeared field operators are the basic entities that are considered in the algebraic approach to quantum field theory. But it's not known whether you can measure them, you can accurately model measurements of these observables by ideal measurement. It's not known. That's an open question. And another point to make is that there are some field theories in which the observables have to be non-local. So in particular in non-abelian gauge theories, the gauge invariant observables are non-local. They're Wilson loops. which are essentially non-local. And you can show that ideal, that there's a paper by Beckman, Gottesman, Kitaev and Presker, which shows that if you can measure these Wilson loops, then that causes, by ideal measurements, that causes superluminosity. Okay. All right. Okay. So the path integral can do everything that the textbook theory can do for non-relativistic quantum mechanics. And also, if you want the usual story, you can reconstruct the usual Hilbert space. So you can take this entity, this path integral, and build the Hilbert space from it. And you can also define operators and derive the Schrödinger equation. So if you want to recover the usual story, then based on this, then you can. But it's more than that. It's a foundational starting point for quantum theory of closed systems. Because if you just forget that this object was defined, I just gave you a story of how this arises by starting with the standard theory and asking what's the probability of the outcomes of the sequence of measurements, then you get this. But if you just forget that this is where it came from and look at this object in itself, then it cries out for an application to a situation where you have a closed system. In other words, there are no measuring devices. You just have the quantum system itself, and that's all. So and there's a familiar fact which is already encouraging that this is the right way to think about quantum theory, which is that if you look at this path integral, when the action is large in units of h bar, this phase oscillates rapidly. And the only time it doesn't oscillate, and therefore when you do an integral over the different paths, those contributions are going to cancel out. So there'll be very little contribution to this integral seemingly. But that's not true when S is stationary with respect to small variations in the path. In other words, for paths which are close to the classical path, the contributions to this integral from this varying phase can actually add up. So the only significant contribution from this path integral comes from paths which are close to the classical path. And if the physical world corresponds to the histories that make the most contribution to this path integral, this will explain when and how classical physics emerges from quantum physics, approximately. Now, the question is, for foundations people, what exactly is this correspondence? How does the physical world correspond to history? What exactly are the rules, the interpretive framework for a quantum theory based on the path integral? Okay. So, to explain the point of view on what the physical world corresponds to in a path integral formulation of quantum theory, I'm going to take a step back from quantum mechanics and talk about classical stochastic theory. Okay. So the basic idea is that quantum mechanics is more like Brownian motion, like a classical stochastic theory, than it is like a classical Hamiltonian theory. So every classical stochastic theory has the following structure. And there's a sample space, which I call omega, of possible space-time histories. And it's good to have an example in mind, so here's a couple of examples. One could be just a sequence of 1,000 coin tosses. And the history is just one particular sequence of outcomes, heads, 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 tails, tails, heads, tails, etc. And there are 2 to the 1,000, for 1,000 coin tosses, there are 2 to the 1,000 elements in this sample space, possible sequences. Okay. Or Wiener paths for a Brownian particle all the possible stochastic linear path trajectories that are Brownian particles. Okay? All of those paths make up the sample space. Then there's an event algebra, Gothic A, and the elements of this event algebra are subsets of the set of histories, and we call them events. So, for example, in the coin tosses case, an event could be the first toss comes up heads. That's an event, and what it is it's a subset of the set of all the histories. What subset is it? It's the subset of all the histories which start off heads and then can be anything else after that. So it's a subset. It's a subset of omega. So the event algebra the elements of the event algebra are subsets of omega. We call them events. Human beings call them. That's the technical term for these subsets of the sample space in theories of stochastic processes. Then there's a measure mu on the event algebra. So give me an event like the first outcome is a head. Then the measure mu is a positive number, and I'll say a bit more about it later. But obviously that's the probability, which encodes both the dynamics and the initial conditions. So for the coin toss, it just encodes the probability of one of the head, for example. And for Wiener paths, it encodes both the probability measure encodes both the dynamics, whether there's drift, for example, but it also encodes the initial conditions where the particle started off, for example. Right. Now, the point of view on quantum mechanics in a path integral framework is that quantum mechanical